Hello everyone, welcome to the game demo series, the place where I would like to share with you my journey of creating small game demos inspired by a variety of well-known games and learning something new along the way. As the first inspiration, I've decided to approach Minecraft. Yeah, another clone of Minecraft. You see, when you approach graphics programming, the next thing after rendering a triangle is actually rendering a cube. The cube is basically a foundation for any voxel-made world, like Minecraft. That said, I think a Minecraft-like demo is a good project to push the knowledge from those tutorials to the next level. I would like to start with the world organization. When it comes to world organization, Minecraft splits the world in chunks of 16 by 16 voxels in width and breadth, and 256 voxels in height. That is actually a lot of voxels. It's about 65,000 per chunk. And if you would multiply this amount of voxels by your view distance, let's say 8 chunks in each direction, it will sum up to 16 million. That's insane. Obviously not all of them are solid blocks, not all of them are visible for the player, so we need to find a way to organize them. For this demo, I followed the Minecraft's approach and created a dense array of blocks for each chunk. Chunks are stored in an ordered map with their relative position as a key, relative to the world center. That allows us to easily query individual chunks for different kind of activities, like object picking. Another approach that you can use to organize your world are octrees. Octree is basically a tree structure that has its children nodes subdivided by 8. This organization works really well for voxel-like worlds and engines, and especially the sparse voxel octree, or SVO for short. SVO allows you to skip entire regions of the world while performing different operations, like object picking or mesh batching. SVO is as well much more memory efficient and faster comparing to the dense arrays approach. But how would you subdivide the voxel world in the SVO? So basically, you grab your entire visible world and keep subdividing it by 8. Up to some meaningful depth. For Minecraft-like world, it will be probably up to 16 by 16 by 16 voxel chunks as your final leaves. So why didn't I use SVOs for this particular demo, if it suits that well? Because introducing octree for world organization comes with some complexity. First of all, our octree needs to be floating, because our world is not static but rather dynamic. While we are moving through the world, we need to update our SVO on the fly by loading and unloading visible and non-visible parts of the world. Second, every time we add or remove blocks in our world, we need to check if we need to subdivide or merge our leaves. And the last one, finding neighbors for each chunk and for each block will be difficult if you have a tree structure, because those neighbors might be in different branches of our tree. So for this small project, I've decided not to go with SVOs and stick to the dense arrays. For world generation, I've used a quite simple Perlin noise generation. It is a great and widely used way to generate continuous terrain. Minecraft also uses Perlin noise for their world generation. They also layer them to get more details and biomes differentiations. I've used noise to generate height map for the terrain and place the decorations. I've simply filled everything that is below a certain threshold with water. Next, culling. As I've mentioned before, we're dealing with a lot of voxels. That said, our GPU for sure won't be happy if we will ask it to render 16 million voxels. So what to do about it? We will need to implement culling of unnecessary geometry. So first optimization that we can enable is the face culling. That will ensure that only visible faces of our geometry are getting rendered. Second, we need to make sure that only visible parts of our world are actually rendered. To do so, we can implement frustum culling. Frustum culling allows us to skip rendering objects that are outside of our camera field of view. Idea behind it is to put your visible objects in simple bounding boxes, like axis-aligned boxes, AABBs, and project a frustum from our camera. Like that, we can run an intersection test between our AABBs and frustum and call invisible objects. To reduce the number of intersection tests, we're only going to test our frustum against chunks and not individual blocks. Like that, we will be able to skip approximately 60 to 70% of our geometry. Even though we're skipping a lot of geometry using frustum culling, we're still sending rendering commands for blocks that are inside of our chunks and are not visible. To address that, we will need to implement mesh batching. The idea behind mesh batching is to group visible meshes into a single one. We need to find all the neighbors for each block inside of our chunks and check if all of them are solid blocks. That will tell us if block potentially can be seen from the camera or not. Doing this check can tell us as well which faces are visible or not. When doing mesh batching, we need to make sure that we check the blocks from neighbor chunks to remove unnecessary seams between chunks. Those seams will not be visible when dealing with the solid mesh, but will definitely appear when rendering translucent mesh. For chunks that are on the border of our visible world, we can load their neighbor chunks but delay meshing them until they enter our chunk's view distance. We can use mesh batching process as well to cache visible blocks and use it when doing object picking. On top of that, we can take it one step further and implement greedy mesh batching. This technique allows us to reduce the amount of geometry we submit to our GPU by grouping faces made of the same material in one single rectangular. However, I was already more than happy with the performance of simple mesh batching, so I decided not to explore that approach deeper. Next one, multithreading. With mesh batching, we created another problem to solve. Mesh batching and world generation potentially are pretty expensive operations. If we profile our world generation pipeline, we will notice that it will take 10 seconds to batch mesh our world on the start of our demo. On top of that, it will take up to half a second to load the new chunks while moving through the world. To address that, we can move mesh batching on the separate thread by creating a chunk job queue and queue runner. We will as well need to protect both our chunk jobs queue and chunk map with mutex to avoid our main thread and runner thread to race for data. By the way, there is a nice trick that you can implement to avoid our chunk job worker thread running all the time. We will add a conditional variable and send a signal through it when we are adding a new job. That will wake up the worker thread and keep it inactive when there are no jobs to process. Lighting. To give some depth to our world, the good idea will be to add some ambient occlusion to it. Ambient occlusion is a technique that lets us simulate how much ambient light reaches different corners or surfaces in our world. Fortunately, in voxel world, it is pretty simple to do. I would like to share with you this paper about ambient occlusion in the voxel worlds. This is a really good explanation on how it works and what problem it basically solves. So check this out. We need to check for each vertex if the blocks that are adjacent to it, neighbors, are solid or not. Sounds familiar? We already do something similar when doing mesh batching, but we need to add a neighbor check for each vertex and not each face. Keep in mind that we need to check it for all of the directions. So I have asked ChatGPT to generate all the possible combinations instead of writing them manually. I still had to arrange them though. Another kind of simple lighting that we can implement is diffuse lighting. Diffuse lighting uses light source direction, for example sun, and normal vector, direction where our face is facing, to calculate our lighting effect. Both ambient occlusion and diffuse lighting can be linked to the day-night cycle in our world. We can shift our ambient and sun colors depending on the time of the day. UI. For UI, we can add a separate layer and handle all its rendering there. We need to make sure, however, that we are rendering it in the pixel space and not in the normalized one. Like that, we can easily adjust any UI part for scaling and its positioning in pixels. Final thoughts. Developing this demo was a nice experience. I managed to learn a lot of different techniques, and I hope that this short recap might be an inspiration for someone else to approach this kind of project. There are ways to take it even further, like adding animated textures for water, identity component system, add basic physics and light sources support, torches and lava. But I think it is enough for this particular demo. If you like this video, click the like button, click notification button. All the source code and additional reading reading materials will be linked down in the description. Thanks for watching, and I see you the next time.